Welcome to crime scene number 1, where we join Dr. Amethyst in gathering evidence about the simple cubic unit cell, or SCC. All the evidence here comes from X-ray diffraction data and mathematical equations. But to make things easier to see, or to make those diffraction patterns easier to see, we're going to use spheres to represent different particles. For us, that's going to be atoms, and lines between those spheres to show the cubic structure. The first piece of evidence is the cubic arrangement of the unit cell based on the crystal lattice's repeated pattern. So as you can see here, we have two views. We have the expanded view that shows the atoms spheres here, and then we also have the space filling view, which shows the atoms actually touching one another to explain exactly what the layers of these different atoms in these crystal structures really are. In SCC, or we can also say primitive unit cell, the centers of 8 identical atoms are going to define the corners of a cube. And in the expanded view, you see it makes it easy to see the cubic portion, but it can be difficult to see the center of the atoms themselves. So we want to make sure we know that this is the center of an atom here, center here, center here, at each of the corners. And there's going to be 8 of them for this cubic arrangement in SCC. In the space filling view here, you can see that the particles touch along the cube edges, but they do not touch diagonally along the cube faces or through its center at all. So with this space filling view, it's going to be easy to see how the atoms are touching and the number of atoms using up the space, but it's actually very difficult to work with and see the inner details with more complicated unit cells. All right, the second piece of evidence that we're going to be talking about is the coordination number. So as you can see, we do have the expanded view down here of the unit cells, and we know they're cubes and they're building blocks. So we have one unit cell here, one here, one here, one here, and that's allowing us to be able to see what neighbors are going to be surrounding a particular atom. So if we count the number of the nearest neighbors from a particular atom, then that'll give us the coordination number. So here we have this atom here, and we can go ahead and count the number of neighbors. We have one here, we have one here, 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 and here. As you can see, there's 4 on the same plane of the atom, 1 above and 1 below, for a coordination number of 6. So far, we have the cubic arrangement, and we know we have a coordination number that equals 6. The third piece of evidence is the number of atoms per unit cell. So for particles of the same size, the higher the coordination number, the greater the number of particles in a given volume. And since we know that one unit cell touches another with no gaps, okay, a particle at a corner face is shared by adjacent cells. So we see this, they're sharing here, and the corner faces are going to be sharing here. Okay, so in SCC, the particle at each corner is a part of 8 adjacent cells. So as you can see, we have a particle corner here, 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 boom, boom, and boom. Again, we saw that over here, how it's going to be a part of 8 adjacent cells. So we can say 1/8 of each atom belongs to each cell. So if we say that 1/8 of each atom belongs to each cell, okay, and we know that we have 8 corners, so that means we're going to have 1 atom per unit cell in SCC. And the fourth and final piece of evidence is the packing efficiency. So we know that crystal lattices are layered. So that means that unit cells result from the way that atoms pack together. So you can kind of think of it as fruit being packed in a grocery store. Okay, so here is our layer of fruit, and the spheres are going to represent our atoms, which of course, in this analogy, is going to be the fruit being packed. So let's pack identical spheres to determine the packing efficiency, which is basically going to be the percentage or total volume of the unit cell that is going to be occupied by the atom spheres, okay? So we basically want to get another little value here, which is going to be packing efficiency, and that's going to be a percentage. It's going to be all based on how these atom spheres are packing in these layers. So for SCC, we're going to arrange the first layer of spheres in the vertical and the horizontal rows. And as you can see, when we are actually lining them up in rows, they form these little diamond-shaped spaces. And so if we place the next layer of spheres directly above the first, as we see in this one, so we have one layer of spheres here and one directly above the first, then we still see that diamond-shaped space. And so based on the SCC arrangement, the spheres are only going to occupy 52% of the unit cell volume. That means 48% is empty, okay? Empty space between these different spheres. So this is basically a very inefficient way to pack spheres. So neither fruit nor atoms, right, are typically packed this way. So all this evidence that we see here is going to contribute to understanding the simple cubic unit cell. And there are usually no common materials with the SCC structure. The only element that can display it is like a extremely rare radioactive polonium. So let's just go ahead and go further and get details about the edge length and density of SCC based on some of this evidence. We now join Detective Emerald to put it all together by getting down to some calculations. So now that we understand the cubic arrangement, coordination number, atoms per cell, and packing efficiency of SCC, let's now use that X-ray diffraction pattern data to provide details about the edge length of the unit cell. So the edge length is going to refer to the length of one side of the unit cell within a crystal lattice, okay? And sometimes you'll see edge length is going to be A, or it can be L, okay, folks? And it is a fundamental parameter that's going to be used to describe the size and geometry of the unit cell that, of course, is going to provide insights into the crystal's structure. So remember, our cubic systems tell us that each side is equal. So if we find one side, or one edge length, we find them all, right? So that's what's pretty cool about being able to use the cubic system as our reference point. We get the edge length from X-ray diffraction data and some arithmetic to find the atomic radii in SCC. So the edge length is going to be A, and that's going to equal to 2R. And R is going to be our radius. So if we wanted to find the radius, then we can actually just use our variables here and manipulate them. So we can say R is equal to A over 2. So if you're given the edge length, then you can use the edge length to then again find your atomic radius. We can also use the edge length to find the volume of a cube, because volume is going to be equal to length cubed. So we can substitute length for A, our edge length, and just cube that to get the volume. Now, knowing the volume and the mass of an atom and the number of atoms per cell in that unit cell will allow us to find the density of an atom. So density is equal to mass over volume, which we know. We know that volume is going to be connected to our edge length, and if we cube the edge length, we can get volume. Now the mass is going to be based on the molar mass of the atom itself. So what are the actual spheres? Remember, the spheres are identical. So it can be any atom. Say you have aluminum, that means you'll get the mass of the aluminum from the periodic table. And it also is going to depend on the number of atoms per unit cell. So in SCC, the number of atoms per unit cell is simply going to be 1. So if we had to find mass, we must take into consideration first 1 atom per unit cell, and we're going to convert that atom to moles. So we use Avogadro's number, and then we're going to use molar mass of the particular type of atom to get the grams per unit cell, which is going to be our mass. And of course, once we have our mass and we have our volume, we can calculate density. Now, we are putting this all together to focus on cracking the case and completing examples, right? So there's going to be a lot of different units that you start seeing when you're doing work with edge length. So for example, the radius is going to be in picometers. And normally you're going to have to convert between picometers and centimeters. So 1 picometer is 10 to the negative 10 centimeters. You also have density, which is grams per centimeter cubed, because we are looking at density of solids. Normally in lab, we see grams per milliliter because we're looking at densities of liquids. So with solids, we have to use centimeter cubed. Also, because we have our grams here, sometimes you can see density in different practice problems given in kilograms. So you would have to convert from kilogram to grams. So 1 kilogram is 1,000 grams. Also, sometimes they may give you meters instead of centimeters. So you will have to convert from 1 meter to centimeters or meters cubed to centimeters cubed because we are dealing with volume. And a lot of times you have to cube the volume, right? And then finally, you want to be able to get molar mass from the periodic table. So you should be able to read the periodic table and get that molar mass. Now, let's do an example to crack the case for a simple cubic unit structure. So to crack the case, let's do an example to connect some information. Note, the questions can increase, basically the questions can increase in difficulty with homework or practice exam because there are many variations to mix these variables. Like there's many ways to mix density, volume, mass, etc. So if you need more practice, of course, you can go to textbook exercises. This question is going to state on screen that it says to identify the characteristics of a simple cubic cell. That's it. So we want to first gather information that we know about the simple cubic cell. And of course, you could have already had a flashcard moment where you put SCC on the front and the different types of characteristics of it on the back. So we know it's going to have a coordination number of 6. We know the atoms per cell is going to be 1. We know the packing efficiency is going to be 58%, right? No, the packing efficiency is totally 52%. Apologies. So the packing efficiency is 52%, and the edge length is going to be 2R. So we can use that to our advantage just when we're thinking about characteristics of SCC. So in this question, all we have to do is find the answer that's related to all these different characteristics. So first, the edge length is going to be 2R. We see 2R here, we see 2R here. So we can get rid of all of these that don't have 2R. Now we're down to B or E. Next, we look at packing efficiency. We know the packing efficiency is 52%, so automatically, yes, is going to be letter B. Edge length of 52%, packing efficiency of edge length of 2R, packing efficiency of 52%, so we are good. We have cracked the case for the SCC unit cell. Let's move on to the next crime scene.